of the things that they had to deal with. And so being facile with naming is important. But the more important thing, in some sense, is what we're going to talk about here, and that is labeling. Labeling is this tentative naming that we give to things to help us understand what's going on. We're going to try to choose terms that are both descriptive and memorable. So that descriptive, so that they tell people at a glance what it is that we're talking about, and memorable, in that we want people to remember what it is that we're talking about. Now, why is this so important? Well, by labeling something, you focus attention on it. So oftentimes there are patterns in the data that you collect in engineering that look like they're important, but you're not sure. But if you're not sure, it's wise to give a labeling to those things so that it helps you remember that that's a pattern that you want to keep your eye on to see if it's important in solving the reference problem. This saves time and reference, of course. By labeling something, you don't have to go through the steps of the phenomenon every time you want to talk about it. But it also is a starting point for further modeling, and it helps the social spread of that concept as something that's important. So this is really key, and it's underappreciated as being important in engineering. We don't talk about it. We should talk about it, and we're talking about it now. For people familiar with iFoundry, many of the terms that we use in iFoundry are chosen to help them spread in exactly the same way. We think it's important, for example, to focus on for example, the term "the missing basics" is a label that helps people think about why it is that we don't talk about these qualitative, critical, and creative thinking skills more than we do. It gives them a name. We don't have to describe them each time, and it helps it stick in people's mind as something important. And over time, as more and more people view it as important, that name becomes a shorthand for widespread social attention. And this is in some sense the point that I was just making. For example, elsewhere we've talked about category creators as being the model engineer of the 21st century versus the category enhancer or optimizer of the 20th century. We've used other terms like Cold War engineer and missed revolutions. To a certain extent, and these terms can be more or less descriptive, and they can be more or less sticky. But another key point to ask is their rhetorical intent beyond their function. So when we use terms like this, we're labeling something so that people remember it. But are we also valuing that something? Are we saying it's good or bad? So when we say Cold War engineer, are we criticizing? When we say missed revolutions, we're saying there's something lacking. And so another key thing to keep in mind is sometimes these terms can be less than neutral. And that's not necessarily a good or bad thing, but it's a point to keep in mind. Now another way to name things is through abbreviations, and acronyms and initialisms. Now let's distinguish these three things. An abbreviation is a shortening of a word or a phrase. An acronym is an abbreviation that can be pronounced as a word, and an initialism is an abbreviation formed from the initial letters of a word. Sometimes people use the word acronym for an initialism. We're going to separate them here to distinguish between the three things. Engineers love to use abbreviations as shorthand, and so for example, we abbreviate Illinois Foundry for Innovation and Engineering as iFoundry. It's a time saver. It's efficient. There are lots of examples of acronyms. SNAFU, situation normal, all followed up, or BASIC, beginner's all-purpose symbolic instruction code, the computer language. So those are initialisms that can be pronounced, and other initialisms can't be pronounced. When we use, for example, when we talked in the communication section about BPR, we were talking about background, purpose, and roadmap, and to talk about BPR, you have to spell it out. Or CSL here at the University of Illinois is the Coordinated Science Laboratory, but no one pronounces it KSL, and nobody says BUPR. Those are not pronounceable. Typically, when you write out the term, like situation, normal, all followed up, you don't capitalize it. But in the acronym, you do capitalize it. And in doing all of this, the key point that we don't want to lose is that by doing this, we draw attention to some important concept, and we hasten its addition to regular conversation about the project. And so when you become involved in a company, you'll find out that they have all kinds of acronyms, initialisms, and abbreviations that you're unfamiliar with because they have sort of a local language of talking about things. And so here in iFoundry, we talk about the MBs or the missing basics all the time, and we do it without explanation. So lots of times you use these things to have a local language. Now let's go back to the tortilla problem and actually part of the problem-solving process. So previously we were talking about names of devices that were already in place at the tortilla plant. But now let's talk about labeling in the tortilla problem. Now recall that the problem was too much dusting flour. And so what labels might we want to assign to this particular problem? Well, to answer that question, we need a model of what it means to have a good label. And I think a good source for that is the Heath brothers book. Dan and Chip Heath wrote a book a couple years back called Made to Stick. And they said that lots of ideas are sticky in human affairs if they adhere to, they have a model of success with one S at the end. If it's simple, unexpected, concrete, credible, emotional, and forms a story of sorts. And so those 6 things make something memorable so that it sticks. And I urge you to look at that book because there are lots of wonderful stories about how different concepts and terms became sticky in ways disproportionate to the terms that were being used and the amount of money that had been invested and so forth. One final thing to keep in mind is that as engineers, with all the math and physics that we study, we think of those things as sort of the ultimate reality. And there is a certain sense in which engineered objects, at least physical objects, have a physical reality. They're made of certain materials, which are certain arrangements of molecules, and that those have certain physical material properties. But once we move from those physical properties to functions, we're on a different ground. When we start to talk about the function of a chair, for example, we're talking about something that's social. Our notion that something has been made to sit in, it depends on the existence of an observer who can sit. And so the key point that I'm making here, and I'm making it all too briefly because it's actually a fairly subtle point that deserves considerably more study than we can apply to it, is that all engineered objects are social. Some engineered objects are physical, but all engineered objects are social because the functions that they have depend on human beings to understand and use those functions. And a favorite source of mine for this kind of thing is the philosopher John Searle's The Construction of Social Reality, who separates sort of brute facts of physics and the physical world from, say, the intentional facts and social facts and institutional facts of a human world. And I think the separation is helpful, but the key point is to recognize that engineered objects, their functions, are always relative to an observer, a human observer. And so when we keep that in mind, we realize that engineering is an incredibly complex thing because not only does it involve the physics, it involves the intentions and behavior of possibly many human beings. Another point to keep in mind is that as we move into a world of the web, more and more engineered objects are institutional, using Searle's term, in a sense that we all must believe them, or some subset of people must believe that the object functions in the way that it does. So for example, an example of that is money. Money is money because we believe it is money. eBay is eBay because we believe it is an auction. And so so this idea that there are kinds of engineered objects that depend on social beings to understand them, to imbue them with their full functionality, is one that is not typically talked about in engineering, but needs to be talked about more. So the bottom line here is that naming and labeling are so commonplace. I mean, language is something that we scarcely give a second thought to, that they're hidden in engineering practice, really in plain sight. Engineering school spends very little time on the names of things. I'm urging you to do otherwise. Naming and labeling, especially labeling, is a critical step to being a great engineer. And when you label things, and you label them well, and you get other people to use your label, you become a more influential engineer. Now, labeling is a first step in modeling, and elsewhere we're going to talk a little bit more about models, but it's a critical step to focusing people's attention on a pattern in data, so that to indicate that that pattern in data may require more attention and more sophisticated modeling, and knowing names and being a good labeler are indeed great first steps to better engineering understanding and better engineering design.